Hello, everyone, and welcome to the VaNTAGe seminar. Today, we're continuing our series of talks on profinite groups and Galois groups, and we're very glad to have Mark Shusterman, who's here to speak about random models of profinite groups in arithmetic geometry and topology. And Mark, is it all right if we record this talk?
Yes, please do. Yeah, thank you.
Wonderful. And everyone, feel free to ask questions during the talk. So, Mark, please go ahead.
Yeah, thank you, Rachel, for the introduction, for inviting me to speak in the seminar. I feel like it's such a great opportunity for me to, in the spirit of the seminar, to talk about some of the open problems and conjectures in the subject. It will be much more about this new kind of perspective in profinite groups. Not so much about results, but about some of the simplest and most natural questions that are appearing in the subject. Um, so so I will first talk about some space of profinite groups where all the action is going to happen. Like a small definition that I'm giving is of a small profinite group. It's just a profinite group such that for any number n, it will only have finitely many open subgroups or equivalently closed subgroups of that given index. On the slides, I gave a slightly different definition, but it's equivalent. Not all profinite groups are going to be like this, but many of the ones we are interested in um, are like this. Maybe profinite completions of some fundamental groups, or maybe a tall fundamental group. Some of the varieties, so some of the examples of profinite groups we care about have this property. And we're interested in, so this is a feature of the subject where we're interested in giving it a topology on this set of small profinite groups, or more precisely, on the isomorphism classes of these groups. So I'll often just say groups and not worry about isomorphism classes. And also everything is going to be in this category of profinite groups where all maps are continuous, all actions are continuous, or all subgroups are closed, and so on and so forth. So everything should be interpreted in this topological sense. And this is somehow the first key definition of a basis on this space. So the way I define the topology. So for me, a basic open set is just going to be the set of those profinite groups which have certain finite quotients and do not have certain other finite quotients. So somehow looking at this profinite group from the above and trying to see what finite quotients do they have and not have. So two profinite groups will be close in this topology, so to speak, if they sort of have a lot of the same quotient. So all of the groups up to a certain size are a quotient in one group if and only if they're a quotient in the other. So that's a topology I want to put. And once I've given this topology, this basic definition, there's already quite a few interesting questions one may want to ask. And those questions are going to be of the form: you're given a certain collection of groups and you're going to compute, you want to compute the closure of the set. So maybe even before that, I'll mention that this space, if you're interested in the property, this space is a Hausdorff, totally disconnected, but not locally compact space. So it's a pretty big space, but at least this has this Hausdorff property, which make it feel like a reasonable topological space. So maybe to give an example of one thing you could compute the closure of, so just like one examples of several, we'll see several examples like this throughout the talk, is a model of groups considered by Dunfield and Thurston, and then further studied by Melanie Wood and Yuan Liu. Is the group of a given deficiency. So you look at all profinite groups where the number of generators minus the number of relations, which is what I call the deficiency of the profinite group, is some fixed number. It could be 0, So no, profinite groups where the number of generators are equal to the number of relations, maybe in some presentation. And you're looking at the collection of all such groups, and the question I'm asking is what is the closure of this collection of groups inside this space? So the point of this question is to try to understand for a certain collection of groups which are interesting from some perspective, like in this case, it's maybe combinatorial group theory because I'm saying something about the relations. For this family of groups, to try to understand which finite quotients can appear and which finite quotients can't appear, and in what combinations. So it's a question that was addressed by Melanie, by Yuan and Melanie. And here's maybe another example, which is more on the topological side. The collection of groups you're considering is the collection of fundamental groups of three manifolds. More precisely, you're taking the profinite completion because you're interested in profinite groups. But the point really is to just understand which finite quotients can and cannot appear for that family. So there will be constraints saying maybe, for example, that if a certain group is a quotient, then a certain other group also has to be a quotient. So in other words, in this language, this collection of groups is not dense in the space of all small profinite groups, but rather it sits in some closed subspace, which could be interesting to describe. Another example from number theory, which is in sort of work in progress by Will Sawin and Melanie Wood, where they look at all the so this is the basically the étale fundamental groups of spectra of a ring of integers of G extensions of the rational numbers. Uh, so in other words, you take a number field, which is a G extension of the rational numbers with some fixed Galois group G, and you look at the maximal unramified extension, and you take the Galois group of that maximal unramified extension over the number field. This gives you some profinite group, which we can show is small. This is basically Minkowski's theorem, or something by Charles Hermite, something pretty classical. And you're interested in what is the closure of that set in this topology we have defined.
Can I ask
Um,
a quick question?
yes, please go ahead.
I'm just curious if you, instead of just asking whether there exists a surjection or there doesn't exist a surjection,
Yeah.
suppose you actually count the number of surjections and then you break up, I
Yeah.
mean, count, does that give you a strictly stronger topology or is it the same?
Yeah, it's a good question. Yeah, right. It will be the same. It will be the same. There's several ways to define this topology. It is definitely very important to count the number of surjections and not just to know whether there exists a surjection or not. So your suggestion is very good, but just for the purpose of defining the topology,
Mhm.
this will be the definition that I gave, which maybe looks a little weird as you're saying, as you're just suggesting, not so natural, is good enough. But your suggestion is really very good. We will see later on in the talk, hopefully, that it is really the case that we're really interested in the number of surjections for some of the finer problems we want to think about. Okay. Yeah. So this is the flavor of the questions, and I also want to give a flavor of the answers. I want to cite a theorem that Melanie and Will prove that I mentioned that describes the closure of this set. So it defines a certain closed subset, which is the smallest closed subset, which contains all three manifold groups, or more precisely, their profinite completions. So it's a quite technical theorem in some senses. It involves a few conditions, but bear with me just to get a sense of what a result in this subject could be. I really wanted to illustrate one of the results. In fact, one of the very few results that exist and is a blueprint for future work in the subject. So those profinite groups which will lie in the closure, they are those that have a certain homomorphism from the third cohomology group to the base, which is Q mod Z, or if you base change by a field, which is going to be a field. And there has to be a few properties that will be satisfied. The first is that the dimension of any cohomology with coefficients in any representation will be the same as that for the dual representation. There is a condition on what cup products must satisfy. There is another condition which is saying that if the representation is symplectic, then the dimension of the cohomology must be even if we're working in odd characteristic, and if we're working in even characteristic, and the representation is an affine symplectic representation, which means that the map to SP of V factors through or lifts to ASPV, which is a bigger group, affine symplectic group, then for some cohomology class, which I'm not going to define precisely, this is CV, the dimension of the parity of the dimension of cohomology is dictated by this cohomology class. So I sort of realize that if you haven't seen this kind of result before, it may look like it's a collection of sort of difficult conditions, which are maybe not obvious at first sight where do they come from, but you can sort of try to see how the fact that it's a three-dimensional manifold, for example, by using the fundamental class, will give you this map tau if your group is the fundamental group of a manifold, and you can try to use the Poincare duality to prove the first condition, and then some more sophisticated math like cobordism theory to prove the other conditions. But what's really striking is that there exists a clear finite set of conditions, which it's not very hard to see cats out a closed subset of this space of profinite groups, which is the exact closure of the collection of three manifold groups. So, this is really quite striking that by giving a finite set of seemingly technical conditions, you can precisely characterize um, the closure. Yeah, so maybe in other words, if you take an open subset which is disjoint from this closure, it means that there will be no three manifold there. If you take an open subset which intersects this closure, you are guaranteed that there will be a three manifold whose fundamental group lies in that set. And some of the problems that I'm going to mention very soon in the talk. So part of the problem will be to understand for various families of groups or various collections of profinite groups how to describe their closures, to guarantee that there exists such a set of conditions. And even though somehow it's a problem, of course, that is defined purely in terms of this topology on profinite groups, the proofs that you have the correct closed subset are often very mysterious or very interesting. They have to do with the topology in this case, or they will have to do with the arithmetic in case you're working with some Galois groups. So this is one very interesting aspect of the theory. So I want to, yeah. Yeah, so I will also want to give more examples of families of profinite groups which we want to study, but for now I also want to talk a little bit about a slightly different aspect, which is not purely topological, goes one step further, and this is measure theory. So I want to also view this space not only as a topological space, but also as a measurable space. I want to give a sigma algebra. And this is, of course, going to be the sigma algebra of Borel sets. You're just taking the all possible countable unions and intersections of these open subsets, of the basic open subsets that we have defined. This is the sigma algebra. And then you can ask some very basic questions, such as those pertaining to the measurability of certain subsets. So one kind of thing you can show is not very difficult, is that the collection of finitely generated profinite groups is measurable with respect to this Borel sigma algebra. And a slightly more advanced question, which looks very much along the same lines, is, but I don't know how to answer it, is whether the set of finitely presented profinite groups is also measurable for this Borel sigma algebra. So maybe there is some simple way to do this, but it doesn't seem apparent to me. I'll mention the obvious fact that finitely generated profinite groups are small in the sense of this definition I gave on the first slide. So we are inside this space S. But the question, yes, Jordan.
Does that mean that you can meaningfully ask what is the probability that a small group is finitely generated, or is this not a probability?
Yes. This is exactly the meaning. Yes, it means that whenever you
That's
define
crazy. Okay.
it's whenever you define a measure, you will be able to do this. That's right. And the question on the third bullet is whether you can ask this for finitely presented groups. And at this point, I don't know yet. This is some reasonably kind of natural question. And a lot of these questions, you can try to simplify them by working with pro-P groups, which are somehow simpler than profinite groups. And even for pro-P groups, it's not wholly obvious to me that the finitely presented locus is measurable. Okay, so and then indeed next, somehow the question that Jordan was building up towards is, can we so what are some interesting probability measures on for this sigma algebra? And all those probability measures, they will basically come from the closures that we've been talking about. So we have some set of profinite groups, such as those with a balanced presentation, or three manifold groups, or Galois groups of unramified extensions. And those are usually some sets which we can traverse in a certain way. We can pick a random element in those sets. So for a three manifold, we have this Dunfield-Thurston model of how to produce a random three manifold. It's basically by gluing two genus G handle bodies along their surfaces by an element of the mapping class group. Yeah, and for G extensions of the rational numbers, we can just pick a random G extension when we order by discriminant or by the product of ramified primes or something like this. So we can go over all the groups in some way, and then that can help us produce a probability, because maybe we can use Dirac measures on these on the groups that we produce, for example, and then just like produce a random group within this closure, and by that get a certain measure maybe that is supported on that closure. That's somehow the basic idea. And so these are the models of Dunfield and Thurston. So, for example, in that model from the paper that was also studied in that paper of Yuan and Melanie, where you are fixing a certain deficiency for your profinite group, there is a fixed number, there is a fixed difference between the number of generators and relations. So the way to pick a random group is to just take a free profinite group and n generators and pick n plus u random independent relations where you can pick them from the Haar measure. This is the thing that very nice about profinite groups, that they have this Haar probability measure, and you can use that to select very random relations. And then you get a certain random group in this way, and then the idea is to take the limit of this measure of this random group as the number of generators goes to infinity, and to show that the limit on the level of measures exists and gives you a probability measure on this space of profinite groups. This was something that was carried out in this paper of Yuan and Melanie. Similarly, I think the next example that I have here is the Dunfield-Thurston model. So I just said how I just gave the topological explanation that you're gluing two handle bodies along their isomorphic boundaries. But there's also a group theoretic explanation, which gives you a very concrete presentation of this three-manifold group. So you take the usual presentation of the surface group. This is the product of commutators equals 1 relation that you see written here. Then you also quotient out by the y's, and then you also quotient out by the images of these y1 up to yg by a random automorphism of the surface group, outer automorphism, which is orientation preserving. So the mapping class group, I can identify it with certain outer automorphism of the surface group, and this way get a very concrete handle on what this random three-manifold group is. Yeah, so you can sample this element of the class group by just doing by performing a random walk on this class group, working with Dane twists maybe, or some other reasonable generating set. This will give you a probability measure. This will give you a random group, and then the main interesting result in that paper of Will and Melanie is that these measures have a limit as the number of generators, as the genus here goes to infinity, as the genus of the surface goes to infinity. So somehow there's like some somewhat mysterious process here that what happens to the measure when you take g to infinity. There is somehow all these measures for every g that are supported on certain g generated groups, but then there is something interesting that happens when you take g to infinity. How is the mass going to distribute as you allow more and more and more and more groups? Sometimes it's still supported, the measure could sometimes still have atoms in some cases. Some certain group could have a positive probability sometimes. In this model, in the first model of a given deficiency, maybe when the deficiency is 0, when the presentation is balanced, the trivial group, for example, has a positive probability. So it's very interesting to study those limiting measures. They have a very different behavior and very interesting behavior if you compare it to measures for an individual G or individual N. Yeah, so now I want to talk about, and this is maybe the part where is more about the open problems, where I want to suggest a few random models, which are also very interesting, maybe inspired by those few models that have already been studied. So maybe the first model, which I find particularly interesting, is the model of the random fundamental group of a curve over a finite field. So what you do, you just take a random element, a random genus G curve over FQ. You take the Dirac measure at that point and you average that. So it's just like picking a random étale fundamental group for a random curve over FQ. And then you take a certain limit as the parameters go to infinity, and you ask the questions that have been basically that I've tried to talk about right now. So what is the closure of this set of fundamental groups, and whether there is a limiting probability measure when you take the limit in this particular way, for example. So I feel it's very interesting to know whether there is some statistical regularity that the fundamental groups of curves exhibit. That's one kind of a natural example.
Mark, do you have in mind here Q going to infinity in a fixed characteristic through powers, or Q just kind of horizontally going to infinity along like larger and larger primes? Do you think that makes a difference?
Yeah, it's a good question. Yeah, so I have been kind of vague here, so I don't have a theorem yet about the convergence, but if I would want to have such a theorem, I would first also have to work with probably with the tame fundamental group. Maybe then I would allow like something which is not tame. But yeah, you're right. These subtleties that you're pointing out may be crucial for whether there is actual convergence of measure or only for on some part of that profinite space. So this is so this is a very relevant. This is definitely a very relevant subtlety. But if I am away from the characteristic, if I just like for example look at the pro prime to characteristic part of the Étale fundamental group, I think it should be fine even if I just let Q go to infinity in any possible way, I would imagine. And then, yeah, I think that's, yeah, so there is interest in both letting Q grow to infinity over the primes and over powers of a fixed prime, yeah. So the next example is from a paper by Jordan and Nigel. So in their paper, I think they only talked about the pro-nilpotent or pro-p fundamental group, but there is no reason in fact, you can do it more generally if you just state the problem. So now what I'm doing is I'm just puncturing the spectrum of Z at like a randomly chosen prime. And I'm looking at the distribution of the Étale fundamental groups of that. It's um, kind of another fairly reasonable model of a random profinite group to consider. There is a subtlety that you are puncturing at a single prime and not in a growing number of primes, because then you can show that the limiting measure will not actually exist. You need to puncture like a fixed number of primes. You can puncture at like maybe 5 or 6 primes, but not, you probably can't allow this to grow. You will even see this at the level of the abelianization. Yeah, so all the models I'm discussing here, they will have pretty interesting abelianizations. And so already from those, you will be able to get some sense of what's going on. And in fact, this whole subject came from some earlier works where people studied distributions of just finite abelian groups. So that's maybe part of the subject which I will not touch. But it was the motivation and somehow part of the technical basis for many of the things I'm mentioning. So another example, yes, this last example on the slide, which also looks very natural from the group theoretic perspective, but actually is also motivated from topology. So here the model is also very simple. You just take the co-kernel basically, or maybe I can say it in this way, you take the co-invariance of a random automorphism of the free group. So you take a free group on n generators, you take an automorphism and you impose the relations that each generator is equal to the image of this generator under the automorphism. This is the same thing as talking about the maximal quotient of the free group on which this automorphism acts trivially. So yeah, so there is a way to cook up a reasonably natural 4 manifold, of which this is the fundamental group, by doing some kind of fibrations with S2 times S1 and drilling things out. It's a little bit of a complicated construction. I will not really go into it here. I will also mention that even in the theory of 3 manifolds, this kind of thing is very relevant. So it's a kind of a topological analog of this model of Nigel and Jordan from the previous bullet point here. So it's an analog in the sense of arithmetic topology. So you're taking basically a three sphere S3 and you're removing a random knot from the three sphere, and you're interested in the fundamental group of that random knot or random link that you're removing. And because links can be basically because links can be viewed as closures of braids. This is some theorem of Alexander from the 19th century topology. You can restrict this model where this automorphism, instead of coming from the automorphism from all the automorphisms of the free group, is just coming from a subgroup, which is the braid group, because you can embed the braid group into the automorphism of the group of the free group. And if you restrict this automorphism to lie in the braid group, then you are getting like a reasonably natural model of random random knots or random links if you want, and their fundamental groups, or rather their profinite completions. And we expect that there will be a way to describe the closure of that set and also to define a limiting measure as n goes to infinity for that set. So these examples, their point is to give some open problems, some questions where I think the methods developed in the papers of many mathematicians, but most recently by Melanie and Will, are going to be very relevant with some extra inputs to be able to address these random models, which to me seem very, very natural. Okay, yeah. So now maybe I want to talk a little bit about how do we know that a limit exists, or how do we show that the limit exists? So I've posed quite a few problems and talked about some existing results. So I want to say a little bit about how one goes about proving the existence of these limits, which is somehow the hardest part, even after you have already figured out what the closure in the topology is for your set of profinite groups. So for that, I need just to make things precise. So when I'm talking about convergence of measures here, I always mean weak convergence. And for this particular topology, this just means that for those basic open sets, the measures converge to the limiting measure. And we don't want just convergence of measures, we want the limiting measure to be also a probability measure. So we don't want anything funky like escape of mass to happen, or any problem like this. So this is part of what one has to prove when showing that these random models give some interesting probability measure. And the key point in this approach, as was pointed out in a question earlier in this talk, is to count the number of surjections. This is what in the subject is called a moment, maybe for a historical reason. So as I said, this subject sort of kicked off from the study of random finite abelian groups. And for those random finite abelian groups, or even for random vector spaces over like a finite field, what I call here, what is called the moment, it basically is just the expectation of a certain power of the size of the random variable. So something which would be called a moment in more classical probability theory, where you study distributions on the real line, for example. Yeah, so these moments are quite often much more accessible than the probabilities of these basic open sets. And these moments often can help you prove the convergence and determine the measure uniquely, especially if you know where it is supported. So it's a strategy that was used or introduced by Will and Melanie in this level of generality, where they show that if the moments do not grow too fast with the group. So every moment is a function of this finite group G. So if the moments don't grow too fast as a function of G, and there is some restrictions on the support of the measures, then you can show that there is convergence, and moreover, these moments determine the distribution. And so what one has to do when trying to prove these questions or solve these conjectures from the previous slide is to try to, the first thing to try to do is to understand the moments. That's somehow the very first thing to do, and then to try to prove that they satisfy certain bounds that are good enough for applying certain techniques that were developed by Will and Melanie. And so I'll close this particular slide with a question that Jordan, in fact, already pointed out earlier, is that because I know that certain events are measurable, the main point is that once I have a certain measure, once I've constructed a measure, I can really ask, as a meaningful problem, what is the probability that a certain group is finitely generated? So it seems like maybe the question should have an obvious yes answer, because all the groups that we have constructed, that we have worked with, they all are finitely generated. We have not seen a single example of a not finitely generated group in this talk. But the point is, in the way we take the limit as n or g or one of the parameters go, or p goes to infinity, the shift to parts of that weird profinite space S of small groups, which are not necessarily finitely generated. It seems like a crazy scenario, but it's still one which is very difficult to rule out provably, I would say.
Mark, we don't know that the unramified Galois groups are finally generated, do we? I thought those were our prototypical example of
Correct.
small groups where we don't know.
Yeah, that's fair. Yes. That's right. We don't know that they are finitely generated, but at least some people expect them to be. So, yeah, that's a very good point. For those we don't know as a matter of fact, and it's a conjecture of Shafarevich. It's a conjecture of Shafarevich that they are.
Right. But that seems impossible. But imagine if we could prove Shafarevich with probability one. That would be amazing.
Right, yeah, and I have some thoughts on how to do this, but I don't yet have a proof of like of like that really is yeah, so it's definitely supposed to definitely should be true that it happens with probability one that things are finitely generated, because in many of those in those distributions, as I said, or at least in some of them, you get the trivial group with positive probability and some other small groups with positive probability, like some finite groups with positive probability. But nevertheless, you can't rule out having a very big profinite group which is not even finitely generated, or at least some of those with positive probability. So this is somehow um, the weird state of things. Yeah. So yeah. So I want to So in the last in my last slide, I want to talk about this computation of moments in a particular case, because I sort of try to convey this idea that computing the moments is one of the key points. So I want to talk about the computation of moments, or an estimate for the moments, for that distribution of Nigel and Jordan that I mentioned earlier, but in the function field case. So let's just recall again that this distribution from the paper of Nigel and Jordan. So I'm puncturing spec z at a random prime, and then taking the étale fundamental group of that. And so now I want to do the same thing over function field. So I'm going to pick a random irreducible polynomial of bounded degree and puncture the affine line over a finite field. at this polynomial or remove the roots of that polynomial. That's what I'm going to do. So this is what I have. Yeah, so this is what I'm doing here. I'm picking a random irreducible divisor. And the way I'm writing it, I'm sort of basically just emphasizing that it's a single orbit under the action of Frobenius. And so I'm removing this divisor, puncturing the affine line, and taking the étale fundamental.
Just to
And I want this.
remember.
And I want
Sorry,
this.
can I ask a question?
Yes, please, please.
I'm just trying to remember, like there's still open conjectures of Abiancar about what this étale fundamental group of the affine line is over FQ, right? And what its finite quotients are.
Yeah, definitely. Yeah, that's a good point. Yes. Yeah, so this is so yeah, exactly. The Abiancan conjectures, they're relevant here. So even over the algebraic closure, so this is over FQ, but even if we talk about algebraic closure, which is seemingly a simpler or maybe more basic question, this étale fundamental group, as you're saying, well, Abiancar conjecture determines the finite quotients, but it doesn't quite determine the structure of the group. And as you're saying, in the case of a finite field quotient, but somehow I want to say is that the part of the magic of that probabilistic approach, and maybe it's also a downside, is that we don't have to have a complete understanding of the very interesting deterministic questions to be able to answer some of the probabilistic ones. So this question that I'm asking here, it could very well circumvent some of the issues in the more difficult, Abiancar style conjectures. And another thing is that probably in everything I'll ever be able to prove, or at least in the near future, I'll usually work with the either tame or prime to P fundamental group, pro prime to P, and in these cases, at least, the geometric fundamental group is sort of known. Is the same thing as it is in characteristic zero. So it's in fact, I'm going to talk here about something which is not nearly as mysterious as what Abiancar conjectured and other people proved after him.
Oh, thanks. It was really interesting.
Oh, okay. So yeah. So now let's just interpret what the G moments are in this. What the G moments are in this particular case. So we need to count surjections, the count number of surjections from this random fundamental group to like a given finite group G. And these are just basically finite étale covers with Galois group G, or if you want, so here I use this geometric perspective, but on the previous bullet point, I use maybe the more traditional Galois theoretic perspective, where you just like want to count Galois extensions with a given Galois group, and you insist on a ramification at a single prime. This is because I have removed an irreducible divisor from the affine line. So these G covers by smooth projective geometrically connected curves, they are parametrized by points of Hurwitz space. There is a Hurwitz space corresponding to this group G, whose FQ points are in bijection basically with G covers, just G covers, not ramified at a single place. This condition is an extra condition that we'll have to take care of separately. And we know that it's possible to try to count those G covers, at least if you forget about this condition for a second, of being ramified at a single prime, it's possible to count this G extensions or G covers by the Grothendieck-Lefschetz trace formula, because we need to count points on a certain scheme or variety or stack over a finite field. And so we have this general machinery of Grothendieck-Lefschetz trace formula and Deligne's Riemann hypothesis, which is very helpful, and comparison theorems between cohomology and characteristic P and characteristic 0 that are proven by Jordan, Ellenberg, and Akshay Venkatesh and Craig Westerland in their paper. They allow us to compare cohomology and characteristic 0 and characteristic P, and eventually we just need to study something about cohomologies basically of braid groups with certain coefficients, or cohomology of Hurwitz spaces more precisely. And recently there has been a great advance in a series of papers by Aaron Landesman and Ishan Levy that computed at least the stable homology of Hurwitz spaces, and this computation allowed them to count points on Hurwitz spaces over finite fields, in particular count the number of G covers without this ramified at a single place restriction. And then in joint work in progress with Jordan, we are putting back this restriction of being ramified at a single place, using this very much same machinery that was used by Landesman and Levy, only that we need a twisted version of it, because we want this extra condition of ramified at a single place. We need to figure out how Frobenius acts on a branch locus. We want this action on the branch locus to be a one big cycle, like a single cycle. And so we need to detect permutations in Sn, where n is the number of branch points that are a cycle. And this can be done using representation theory of Sn. We know that every conjugacy class, every function that is invariant under conjugation, can be expressed as a linear combination of characters of irreducible representations, for that matter. In our case, these representations are wedges of the standard representation. And by computing the cohomology of Hurwitz spaces, or again, at least the stable homology for those for those Hurwitz spaces twisted by those representations of the symmetric group, we are able to get an estimate for those moments, where there is a certain caveat where we only get the moment once the size of the finite field is large compared to the order of the finite group G that we need the moment for. This is not enough for all the applications that you want in this probabilistic setting, but at least it's some progress. We definitely would want to have it for fixed Q and all G, but the machinery that we're using of homological stability does not seem to be maybe sufficiently developed for that, because there is unstable cohomology, and the bounds on that cannot possibly be strong enough to allow for applications as strong as for the results as strong as we need for this random model of profinite groups, but at least it's some indication of what's going on. I would also like to mention work published recently by Zachary Himes, Jeremy Miller, and Janie Wilson that obtained results which are pretty similar to the ones we are still working on with Jordan, with some restrictions on the finite group G. So also using the methods of homological stability, and some recent developments on uniform homological stability. Okay, I think that's all I wanted to say. I'm right in time to finish. I think. Thank you so much for all the attention and the questions, and I'm happy to have more discussion and more questions if you have any.
Thank you. Well, this is a great time for some questions. Jordan, do you want to?
I have a couple, but I don't want to. Okay,
Mm.
I'm gonna ask one, and then if that requires somebody else ask, they can ask, and then I'll ask my second one. Okay, so question one is, if we were like studying equidistribution in like Rn or something, like one thing we would do is have like lots of processes that produce like lots of points in Rn, and we could ask like, do those larger and larger sequences converge to like some distribution? But in reality, on Rn, we have some notion of uniform distribution in mind from the start, and we often ask like, do these larger and larger sequences of
Yeah.
points converge to that? So, I mean, I guess my question is, do we think there's any prospect of having some intrinsic notion of a quote, quote, uniform distribution on the set of isomorphism classes of small groups where we can ask, now these guys would presumably not converge to those because, for instance, in Melanie and Will's thing, presumably not all small groups satisfy those weird conditions, or else we wouldn't know it. But then you could ask, okay,
Right.
is it random conditional on? So is there, yeah, I guess I talk too much, but do we think there is a quote, quote, uniform distribution on small
Yeah.
groups?
Yeah, I think I want to say no. The reason why I want to say no is because of this weird property I mentioned in the beginning of the talk, which makes me think it's a no. This property that the space is not locally compact.
Oh,
It seems to me, and this closed subset from Melanie and Will's paper, I think, is also not locally compact. So it's very hard to imagine. It's like a very big space. So you somehow have to make a decision of where this probability measure is going to be in a way. So it's for that. Yeah, it's I agree that if you're in the interval, in the real interval from 0 to 1, there is a good notion of a uniform measure. But yeah, but even on the real line, in some sense, there isn't really a notion of I feel like a uniform probability measure for that matter. Um,
true. Yeah, that's fair.
yeah, and that's yeah, and this is the difference between compact and locally compact, I feel. And if it's not even locally compact, it's kind of maybe there is, yeah, I can't say for sure. Um, yeah.
I mean, I
Yeah,
guess
there's
even on the abelian, a small profinite group it's not obvious that there's a nice, kind
yeah,
of
exactly, exactly.
Hmm.
one measure that's the best.
I don't
Right.
know. Don't you think their Cohen-Lenstra measure is the best?
Sorry, which one?
Oh, I guess
Cohen-
that's on finite. Okay, I gotta think about it. Maybe I spoke too rapidly. Um,
Anyway, so yeah.
Yeah, what I thought in that direction is maybe like you can imagine there's the space of measures, and then there's like I guess you can talk about like the space of measures, and you can talk about like the extremal points of that space because you can take like convex combinations
hmm.
of the probability measures, and maybe the extreme points they have some meaning of like some measures that control all the other measures, but it just still feels to me that there will be too many. And you can see here in the examples that like every other example, which is like reasonably interesting from topology or arithmetic, will give you a completely different, or like they're all related in some sense, but still somewhat different measure. Yeah, so
Okay, my second question is even less well-formed than my first question. So unless somebody stops me, I'm going to ask it, which is, I find this result of Will and Melanie's very striking that you have this kind of, so to speak, finite description of
yeah.
the closure of this kind of large infinite class of profinite groups.
Yeah.
And what it reminds me of a little bit, and now I'm embarrassed, I forgot the name of this theorem, but there's like a graph theory theorem that says that if you have a condition on graphs that's closed under minors, there's some finite list of excluded minors that delineates that.
You're right.
It,
It's like planar graphs, I think. Planar
right,
graphs.
it's like
Yeah.
a massive generalization of this fact about planar graphs, right? That if you
Yes.
so I just like completely wildly, I wonder, do we think there could be some notion of a good class of profinite groups where even if we don't know what it is, we sort of somehow know a priori that there's sort of some finite length description of its closure. That's what it reminds me of, where I'm like, oh,
Oh,
maybe you have
right.
to figure out what it is, but um,
Yeah, right. That's a good point. Yeah, right. Because it's not just the closed set. It's a closed set which is given by a finite list of
exactly. Like there's some kind of there's But I mean,
Oh,
but I don't even know what I mean by finite description in this because it's not like it's not as simple as like a
all
list
right.
of excluded quotients or something like that. I mean, yeah.
No, but it's an interesting observation. Yeah, yeah, I know. I didn't think about it, but yeah, I'll definitely ponder about this. Yeah. Definitely in all kind of, I agree that in all cases that we are interested in, there like must be a finite description. I mean, it's
Oh, it's the Robertson-Seymour theorem. I looked it up. That's the name of the theorem. I forgot that I was quoting the Robertson-Seymour theorem on graph theory.
okay, cool. Yeah.
Can I ask another weird question? Um, I remember that in the abelian case, when you if you take that Liu Wood random
Yeah.
measure,
Yeah.
but you do it in the abelian case, then that's the one where you choose if you fix a number u and
Yeah.
you take the free group modulo, well, in this case free abelian group modulo n plus u generators.
Yeah.
I remember that you can take the just because you can compute everything explicitly in the abelian group case, you can make sense of it not just for integer values of u, but also for real numbers u, well, u greater than something. And I
Yeah,
was
right.
wondering whether the same thing happens in the non-abelian groups, whether you can
Right.
define.
Yeah, very good question. Yeah, I somehow have to admit that I don't remember if I saw this in their paper or not,
Yeah,
but my
maybe they already did it. I don't remember. I just don't.
yeah, right. But my guess is that their paper gives the formulas for the probability. And
Mhm.
so you can, yeah. And so basically what you can do is you can sort of, yeah, you can extrapolate these, you can plug basically,
Okay.
and
Yeah.
there's a chance that it will work. And there's another way to do it, which is like they give formula for the moments, and you can plug any u there in the moments, I feel. And you can also try to prove
Mhm.
using this general theorems of Will and Melanie that because the moments don't grow fast enough, there will be a unique measure. So I suspect that the
Yeah,
answer,
that makes sense.
yes. Yeah, I mean, yeah, that's a good point. I mean, many of the things I've been talking about are like secretly non-Abelianizations of things that were already known in the abelian case. Like, for example, that other model that I gave for like random 3 and 4 manifolds, which I wrote in this group theoretic way. This is basically there's this model where you take a random like invertible matrix and you take the co-kernel of that matrix minus the identity.
Mhm.
That's all. That's also like gives you Cohen-Lenstra distribution basically. And so this is basically just like a non-abelian version of it, which ends up being pretty natural both in like group theory and in like 3 and 4 dimensional topology. So yeah, so it's like a lot of the things that this subject does are like pretty much inspired by the abelian case.
Thanks, Mark.
Yeah,
Uh,
thank you so much for inviting me. It was really fun. Yeah, thank you.